All right, folks, welcome to lecture 3, which is titled The Relationship Between Two Variables. So to start off the lecture, let's first review the measures of spread and central tendency. So what measure of central tendency is particularly sensitive to outliers? And if you recall from last week, we said it was the mean. And the reason for that is if you have a particularly big or small outlier, what the calculation does is sort of bias that mean towards whatever that large or small value is, right? So it sort of distorts things. And in this case, you would want to use the median as opposed to the mean. Now, the next question is which measure of central tendency is less useful when values are measured to many digits, right? And so that would be the mode. So an easy interpretation of the standard deviation is that it is basically the blank between a data point and the blank, right? And so this is just the typical distance and mean. So in sum, an easy interpretation of the standard deviation is that it is basically the typical distance between a data point and the mean. So with that review out of the way, we're going to start the lecture by first talking about associations among variables. And so far, what we've mostly focused on are tools to help us describe a single variable at a time. But what we want to transition into is our thinking towards two variables jointly. And so a common thing that we hear thrown around are words like association, related, or correlated when we're describing two variables. And so the statistical tools we'll use to describe the relationship between two variables will depend on whether our variables are quantitative or qualitative in nature, right? So there's no one size fits all in learning about the relationship between two variables. So you may be wondering, which measure of association do I use when trying to analyze data? Right, so this table provides a decent overview of what you do in each case. So let's say in the instance we have one quantitative and one qualitative variable, we would go about measuring the means or the medians across groups. That would be the way that we measure association in that case. The second is the case if we had two qualitative variables. And for that, we would use a contingency table or crosstabs to compare different rates across groups. Now, if we had two quantitative variables, we would use correlation and regression. And that's actually going to be the focus of the lecture for today. Now, ordinal variables can actually be treated as quantitative or qualitative. So you can calculate a mean or a correlation with an ordinal variable, but that requires you to assign specific numerical values to the ordered response options and treat the variable as though it's discrete or continuous. Alternatively, you could always treat an ordinal variable like a qualitative variable, but this can make the analysis slightly more complex. Now, we'll start off with the case of one quantitative and one qualitative variable. And so an easy example we could look at are comparisons between charter and traditional schools. So this should be a little bit familiar from what we did in the homework last week, but our continuous variable or quantitative variable we're interested in is the pass rate. And now then the school type, whether it's a charter or traditional school, serves as the qualitative variable. And so what we can essentially do is calculate a median or mean pass rate for each category, and then we can compare these values to see which of the two groups has a higher typical pass rate and how big the difference is. So in this slide here, I took the summary statistics for the pass rate if the value of charter was equal to 0, right? So those would be traditional schools. And here I'm summing the pass rate if charter schools are equal to 1, so charter schools. Right, and what we can clearly look at here are differences in observations, differences in mean values, and differences in standard deviations. So what does this actually tell us? Based on this output, we conclude that traditional schools have a higher average pass rate than charter schools. And a more specific way of saying this is that the pass rate is about 4 percentage points higher in traditional schools. Thus, we would conclude from this analysis that the two variables are related in some way. Also, if we looked at the standard deviations, we can also conclude that charter schools have a wider spread or a less consistency in their test scores than traditional schools tend to. So instead of using the mean values, we could also compare median pass rates, right? Maybe what's happening here is there's an outlier that's sort of distorting our perception of the relationship between these two sectors. And so using medians might actually be better in this case. Right, so here's the example again if we take the median. And once again, we see traditional schools have a higher median score than charter schools. And ultimately, it provides a pretty similar result. So it doesn't seem like a skewed distribution is too big of a problem in this case. And so the median pass rate is actually 4.5 percentage points higher in traditional schools than charter schools. Now, besides doing this with a table, we can also use a visual depiction and basically reach the same conclusion. Right, so here's a box plot. And once again, we can see that the median score is higher for traditional schools than it is for charter schools. Right, so basically getting the same information but graphical, right? So maybe some people interpret these findings easier with a graph. Maybe some people understand it better with a table. So now we have the case of two qualitative variables, and we would use crosstabs or contingency tables, right? So we have an example here of who lives on campus. So we have a 2x2 table if someone is an underclassman or an upperclassman, and if they live off of campus or on campus. So when you're given a crosstab like this, you should focus on the percentage listed, and this is really similar to just comparing the means, right? So based on the table in the prior slide, underclassmen live on campus 65.2% of the time, while upperclassmen only live on campus 5.6% of the time, or a roughly 60 percentage point gap. And so based on this analysis, we conclude that living on campus is much more common among underclassmen. Thus, we would again conclude that these two variables are related, since the percentages in row 1 differ from the percentages in row 2. Right, so let's look at row 1. See pretty stark differences here. Here in row 2, even starker. So now for the case of two quantitative variables, we'll use correlation, which is a statistic that's used to describe the relationship between two quantitative variables. And so correlation actually tells us whether higher values in one variable predict higher values in another. So we'll start with just a simple graph, and these actually provide, I think, the best teaching tool to understand and visualize correlation. Right, so one common thing that we've done is graph two quantitative variables using a scatter plot. Right, so we have a continuous variable on the x-axis and a continuous variable on the y-axis, and we just sort of see how they look. Now, the important thing to know about correlation is that it always falls between -1 and 1. And so to really visualize correlation, what I want you to do is think about drawing a straight line through the data and seeing how closely the data actually maps onto that line. And if you were to do this and the data fell perfectly along a straight line that points upward, that would mean that the correlation will be 1. Now, if the data falls perfectly along a straight line that points downward, the correlation will be -1. And if the two variables are totally unrelated to one another, the correlation will be 0. So here's a graph of a positive correlation of 0.72. Right, so we see if we were to shoot a line here, everything would fall fairly close to that line. And here's one going the opposite direction, -0.67. And here's one with really no correlation, right? It's unclear how we shoot the line through this data, right? It's basically a spurious relationship. So a little cheat sheet that you can rely on is dividing the dividing a plot into 4 quadrants. And that indicates whether the data point is positively or negatively contributing to the correlation, right? So things in the top left and bottom left are negative. Things in the bottom left and top right are positive. Yes, so if most data points are in the upper right and lower left quadrants, the correlation will be positive. And likewise, they will be negative if all of them are in the upper left and lower right quadrants. Now, if the data is spread fairly evenly among all quadrants, the correlation will actually be close to 0. And so weaker correlations are harder to visually detect, but ultimately, I think the quadrants can serve as a good way to figure out what the correlation is without any specific tools, right? So you can just basically do this by eyeballing it. Exactly for sure what the correlation is here, but we can see that in general, there are more dots here and here, right? So 3 data points for negative compared to 6 for positive. Now, one thing that you might be wondering is how the steepness of the line relates to correlation. And it actually doesn't matter at all, right? So here's a correlation of 0.98. If we were to shoot a line through this, it falls super close. And here's the exact same thing, right? The steepness changed, but the correlation hasn't. Right, and so here's another example that the steepness in part depends on how the axes are drawn. So this is actually the exact same data point from the prior slides, but with a different y-axis. Right, so these are the exact same thing, but we're sort of changing the steepness. Right, so steepness doesn't matter for correlation. Now, if the data appears to follow a pattern, but the pattern is not in the form of a straight line, there's actually what's called a nonlinear relationship. And so nonlinear relationships may produce correlations of 0 or close to 0, even if the 2 variables are strongly related to one another. And so here's some more examples of just weird correlations, right? Like even though there's a clear pattern in these, if you were to use a correlation statistic, it would all be 0, right? And then these are sort of the more standard correlations that we've already encountered, and generally what you would encounter in the real world. Now, as we transition out of correlation into regression, I want to first introduce some important concepts, right? So I've mentioned this a little bit in the past, but there's the idea of the unit of analysis, which is the unit of interest in an empirical study. And this is typically represented by a single row of data in a spreadsheet, right? Whether it's an individual, a group, period in time, so on and so forth. Now, the independent variable is a variable that affects or explains another variable. And the dependent variable is a variable that is affected or explained by another variable. So we use an independent variable to predict the dependent variable. And so what linear regression does is essentially draw a line through some data, like this. And we're basically calculating the slope of that line, right? So as this should be familiar to a lot of you, to write the equation for a straight line, we need to know the y-intercept and the slope. So in math class, you might have seen lines represented as y equals mx plus b, but for the purpose of regression, we'll use the following notation. A is equal to the intercept, or the constant. B is the slope, which calculates the rise over run. And then it's assumed that y is the dependent variable and x is the independent variable. And so once we've estimated our line, what we normally care about most are these values of a and b. And a and b are what are referred to as regression coefficients. And in general, we tend to care more about B, which is the slope, since it tells us something about how the two variables are related to one another. If B is a positive coefficient, a 1 unit increase in the independent variable predicts a beta unit increase in the dependent variable. And if B is negative, it predicts a beta unit decrease in the dependent variable. And so I'll go ahead and give a couple examples here to make this a little bit clearer. So the first one we're going to do is predict university grades, which is found on chapter 3 in the textbook. And so our dependent variable in this case would be the university grade point average, so measured as their GPA, basically just how good their grades are. Their independent variable is the high school GPA. So really we're asking, how much better do I expect a student to do at university if they had a high GPA in high school? And so in Stata, I'm going to pull up this data and run a scatter plot of the two variables and then a correlation to get us started. All right, so let me just pull up the do file real quick. I'll run the two-way scatter and the correlation command at the same time. So here's the scatter plot, right? It seems pretty clear. We have a strong positive correlation here. Higher values of high school GPA predict higher values of university GPA. But we don't know how strong this association is, so let's check our Stata output to see what the correlation coefficient is. All right, so that's a pretty strong correlation of 0.78, which suggests that there's a really high level of association between the two, right? If we draw a line through that, we'll see a very straight line, and there's not a lot of deviation off of that line. All right, so we can see there's a strong correlation, but this still doesn't actually tell us how much higher the university GPA is expected to be if the high school GPA goes up by a point. So in essence, we still need to run a regression. So now we're going to run the regression command, and then we're going to run a two-way scatter plot with the line fit through it. So we'll open up the do file again. We'll run the regression command first. We'll do this one at a time. All right, so in Stata, what we have here is the constant value. We have the slope of the high GPA variable. And what we'll essentially have to do is, or essentially what this suggests is that for every 1 unit increase in high school GPA, it predicts a 0.67 percentage point increase in one's university GPA. And another way we can go about disentangling this is through the two-way scatter plot. Now this is literally just a graphical representation of that table that I showed you. Right, so this slope, or this increase is the slope, and what we could do is plug in specific values of a high school GPA to see what it predicts for a college GPA. All right, so just to review this, the coefficient for high school GPA is 0.67, so a 1 unit increase in high school GPA predicts a 0.67 point increase in university GPA. And so we can actually write the function for our estimated regression line by substituting our coefficient estimates into the regression model, right? So if you recall, the original model is y hat equals bx plus a, right? So this is the predicted value of college GPA equals 0.67, that's the rise over run, times one's high school GPA plus the constant of 1.10. So we can actually plug and chug a lot of this by hand and substitute in values to see the expected university GPA for different high school GPAs. Right, so now that we have our equation here, for someone with a high school GPA at 2.5, we predict that they'll actually have a GPA of 2.78 in college. Now for someone with a high school GPA of 3.5, we estimate that they'll have a GPA of 3.45 in college. Now to close up, there's a distinction here between correlation and regression that I think is worth going over. So regression coefficients, much like correlation coefficients, tell us something about the relationship between two variables. But correlation and regression coefficients are interpreted differently. So a correlation coefficient tells us how closely the data fall along a straight line. Regression coefficients, on the other hand, tell us what the line looks like. So the B, the rise over run, is telling us how steep that relationship is. And so both actually allow us to draw conclusions about whether two continuous variables are linearly associated with one another. It's important to know that the correlation coefficient and the regression slope coefficient will always have the same sign, either positive or negative, but their magnitudes are usually different. Right? Regression coefficients aren't bounded by -1 and 1, whereas the correlation coefficient is. Now the next topic that I want to sort of bring up is the topic of standardization, which arises when the case that it can be useful to convert a variable in a data set into a different scale. And what this normally does is give us a mean of 0 and a standard deviation of 1. And so what standardization does is converts a variable so that its values indicate how many standard deviation units each data point is from the mean of the distribution. And what this does is produce a z-score, which is how we refer to a variable or data point that has been standardized. So here's an example above where we have a regular distribution of data, and then we standardize it. So what standardizing does is it doesn't actually change the shape of the distribution. It just subtracts the mean from the distribution so that it's centered around 0. And then you divide by the standard deviation, which either stretches or squishes the distribution so that the standard deviation is equal to 1. Right? So you calculate a z-score by taking the value of x, subtracting the mean, dividing by the standard deviation. And z-scores allow us to make comparisons among distributions with similar shapes, but different means and standard deviations. So one example is that with a standardized unit, we can compare two students, even if one took an SAT and the other took the SAT, right? So we are able to make comparisons across different measurements. Another type of transformation is a logarithmic transformation, which can be used to make outliers less pronounced. And especially if this is on the right side of the distribution. So they're extremely large values. So think of the case of housing prices, for instance, right? If you have some houses that are millions and millions of dollars, but most houses are more in a modest price range of anywhere from $100,000 to $200,000, right? A logarithmic transformation could be useful here. And an important caveat is that logging variables can help with outliers, but they're generally harder to interpret. And so here's an example from average teacher salaries before the logarithmic transformation, right? We see an outlier up here, someone that makes over 80,000, and then we see some other people that kind of sit outside the distribution here. So what we want to do is maybe pull down the influence of these values and boost up the influence of everything that sort of sits within the distribution. And this is what happens after we take the logarithmic transformation. Notice how everything is on a smaller scale and things are much more condensed, right? So now, instead of the difference being 60,000 to over 80,000, it's about 90,000, right? We see the difference gets from about 11 to 11.4, right? So it really does a lot to shrink that distribution down. And another way that we can look at this is comparing the means to the median, right? Because remember, if the mean was greater than the median, that could be evidence of a right skew. And so we see this here, right? We see some evidence of a right skew. But look what happens here after the log transformation, right? That median and that mean are about equal, right? So it removes that skew pretty considerably.